Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Applied Electronics. Today we are dealing with the subject Semiconductor Devices and Integrated Circuit of semester 4. Today we are going to discuss unit 4. The topics that we are going to discuss in unit 4 are metal semiconductor junction, that is MS junction, how the MS junction energy diagrams and the characteristics, how the barrier will going to form in MS junction, all these things that we are going to study in MS junction, and the Schottky effect, the depletion layer, and the metal insulator semiconductor diode, that is MIS diode. Let us start with the metal semiconductor junction. This metal semiconductor junction will formed by sandwiching the metal with semiconductor. So, we need to know about the energy diagram of metal and as well as semiconductor. There is a difference in metal and semiconductor energy band diagram. So, this will going to change the properties when we are going to make contact of metal and semiconductor. The energy band diagram of metal as well as semiconductor is different when it is apart and when it is in contact. So, all these things to make us to observe some of the characteristics, what are the changes in parameters of energy band diagram. So, all these things we are going to discuss in a MS junction diode. First thing, that this is how the MS junction looks. This MS junction will have a metal and a semiconductor. This is called as ohmic contact. Why? Means because there is no potential exist between metal and the semiconductor here, that is why it is called as ohmic contact. This is a metal and semiconductor. Here we can observe the Schottky barrier that we will study later, how the Schottky barrier is going to form and how we are going to reduce the barrier. This effect is called as Schottky effect. We will study in depth in the next upcoming slide. This is a cathode where the electron injecting. This is a cathode where the electron injecting, this is having a low work function for metal, and anode is a hole injecting contact, high work function metal. This is a high work metal function. So, this is having this contact have high work function. Then XT is the depletion distance, the depletion layer is formed inside the semiconductor, that length is expressed in XT. Next we move on to flat band diagram. As I said, the MS junction characteristics can be studied with the help of energy band diagram. So, we need to know how the metal energy band diagram and the semiconductor band diagram is different, and when it is in contact and when it is not in contact, what are the observation we can make. So, in a metal before contact, the metal energy band diagram will be like this, where the Fermi energy, the Fermi level of a metal, EFM represent the Fermi level of the metal. This will be merged with the conduction and valence band. So, conduction band and valence band are merged in a metal, but here in the semiconductor, the Fermi energy, the Fermi level, the Fermi level EF is near to the C, that the conduction energy band. This is the conduction energy band, this is the valence energy band, this is the Fermi energy band, this is closer to the conduction energy band. The symbol chi indicates the affinity of a charge. This phi m, the phi m indicates the work function of metal, the phi m indicates the work function of metal, and when it comes to contact, when the metal and semiconductor comes to contact, how the energy band diagram looks. This is how it looks. When the metal and semiconductor come into contact, there is a flat band. This is a flat band barrier. We can observe the flat band barrier when it comes into contact. This phi b is the barrier height. This phi m is a work function of metal. This chi indicates, the symbol chi indicate the electron affinity of a semiconductor. So, soon after when we make a metal and a semiconductor, there is no much difference, there is no much changes in a metal and semiconductor. Probably there is a changes that we study on a later when we consider thermal equilibrium condition. There will be a changes occur, not soon after the metal and semiconductor are in contact, but later after some time there is a changes in a energy band diagram of metal and semiconductor. The flat band conditions, from when we are make a contact of metal and semiconductor, we need to observe some things from the flat band diagram. That is, one we are going to find out is a built-in potential and also the barrier height. We know that barrier is formed due to the formation, due to the contact of metal and semiconductor. So, how we are going to calculate the barrier height and also the built-in potential. So, first the barrier height, how we are going to find the barrier height? As I said, phi b represent the barrier height, and the phi b is defined as a potential difference between the Fermi energy of a metal, that is phi m. This is the Fermi energy of a metal, and the band edge where the majority carriers this chi. This is a chi. Chi indicates the band edge where the majority carriers reside, or the semiconductor majority carriers reside. This phi b minus chi indicates the barrier height of a n type semiconductor, whereas in p type the barrier height of a p type is Eg, that is energy gap, the energy gap divided by q, the charge, plus chi minus phi m, the work function of metal, for p type semiconductor. So, we come to know the barrier height of a n type material and as well as a p type material. The phi m is a work function and chi is a electron affinity. Next, another thing that we are going to find out from the flat band condition is built-in potential. Due to this contact, there is a potential created in the barrier. So, how we are going to know the barrier potential? With the help of formula we can find, where phi I is the difference between the built-in potential is represented by phi I. It is a difference between Fermi energy of the metal phi m, the Fermi energy of a metal, and that of the semiconductor. The semiconductor and the metal difference, Fermi energy of the metal and the semiconductor difference gives the built-in potential, that is represented by phi I is equal to phi m minus chi minus E c minus E f, that is conduction energy and the Fermi energy of n type divided by q, whereas in p type phi I is equal to chi plus E c minus E f of p type divided by q minus phi m. This is for p type. These are the two things that we can find out from the energy band diagram when it is going to when the metal and semiconductor are in contact. We find the flat band diagram. From this we can find the barrier height as well as built-in potential. So, built-in potential is very important because the built-in potential gives us a initial voltage that we need to apply for a device to make a conduction. So, this is the table shows the barrier heights of a different Schottky metals. The metal is called as Schottky metals, since it will, these metals will create the barrier when metal and semiconductor are in contact. This is n type silicon. For aluminum metal and n type silicon, it is 0.7 electron volt. The barrier height is measured in electron volt. So, for p type silicon, for aluminum metal it is 0.8. Similarly, it will varies for different Schottky metals and different semiconductor devices. Next, we move on to another condition of MS junction. Till now we studied the MS junction which is a flat band mode, flat band condition. But when it is in equilibrium, when there is no voltage, soon after the metal and semiconductor are in contact, we studied the flat band condition. But as I said, it is not always flat, there is some slight variation. Why the slight variation? This is the flat band diagram that is we observed, but due to the thermal equilibrium, that is due to some internal chemical reaction, the energy band diagram will going to vary. This energy band diagram is represented here due to the thermal equilibrium. The phi b is varied, the phi b is decreased, it is moving upward, and the phi I, the built-in potential is also decreasing. And the Fermi level of the metal and as well as semiconductor, here you can observe it is almost in the same level. This is the thermal equilibrium condition of MS junction. Why this condition occur? Because when the metal and semiconductor is in contact, the electrons in the majority electrons, if you consider the n type, the majority electrons will going to move to the metals, because here it will be of higher potential due to the majority free electrons, available free electrons. This is trying to move to the metals to the diffusion process, and the holes from the metal to the semiconductor. This will create a equilibrium till the holes and electrons concentration are equal. After once it reaches the concentration of equal concentration on the both the side, it reaches the equilibrium state. The Fermi level of a metal and semiconductors are on the same level. Next, due to the formation of a Fermi level, that having the in the equilibrium condition, we also observe one more thing, the depletion region formation. The flat band is now it is bended due to the diffusion process of the electron movement from the n type to the metal, or if it is p type, the holes will want to move. So, due to this, if n type we consider, the free electrons will move from the semiconductor to the metal, leaving behind the positive donor atom. So, this donor atom will create a barrier. This barrier is called as potential region. Next to the metal contact, there is existing of a some barrier due to the positive donor atom. That region is called as depletion region. When the depletion region is created, the remaining electrons will not move or will not able to cross this depletion region. This is how in the thermal equilibrium condition the depletion region is formed, and the potential across the semiconductor equals the built-in potential. So, due to this depletion region, there is a low, the potential in the semiconductor will be lowered. So, this is the built-in potential of a semiconductor. Phi I indicates the built-in potential of the semiconductor. So, we need to break the depletion region, means we need to apply a potential that is equal to this phi I. Next, the MS junction in forward bias. What happens if the MS junction is in forward bias? This is before the, that is what we get from the equilibrium. When we give a positive potential for a metal, there is existing the results in a smaller potential drop across the semiconductor due to the application of positive voltage. So, this makes the diffusion and drift is disturbed due to this potential that what we applied, the diffusion and drift are disturbed, and more electron will diffuse toward the metal than the number drifting into the semiconductor. So, the more electron will flow from the semiconductor to metal than drifting inside the semiconductor. This leads to a positive current through the junction at voltage comparable to built-in voltage, and we observe here there is a VA. This is what the voltage, due to the small voltage only the disturbance of drift and diffusion occurs, so that the current will going to flow in the junction. Let us have a short break. Welcome back after a short break. Before break, we are discussing about the forward bias of MS junction. Now, learning about reverse bias of a MS junction. So, this is how the reverse bias in equilibrium state, the energy band diagram looks. And this is how when we are going to give a reverse bias, reverse voltage for the metal. When we give a reverse bias to the metal, we can observe the Fermi level is just below the conduction band and it is coming lower. So, there is a barrier existing, the existence of barrier here, this will indicate the barrier. So, the barrier is existed and it is too large. This indicates the depletion region width is increasing. So, the resistance also increasing, the possibility of current flow is none. So, there is no possibility of current flow due to the reverse bias, and we are getting a barrier, the barrier height also increases. The semiconductor junction with positive barrier height as almost acts as a rectifying, and it is having a rectifying behavior. When we give a positive bias for a MS junction, it almost acts as a rectifying device. A large current exists under the forward bias and there will be no current in a reverse bias. Now, this indicates, this is a comparison that we can make in a forward and as well as reverse. In the forward, the Fermi level will go touches to the conduction band and the barrier height will be much lesser, and when it comes to this, the potential, the built-in potential less here, but here the potential increases and also the barrier is also increasing, the conduction band is lowering down. So, this indicates that only in the forward bias the MS junction will conduct and in the reverse bias it won't conduct, and the potential across the semiconductor therefore equals the built-in potential, that is what the phi I, phi x equal to infinity minus phi x equal to x of phi x equal to infinity minus phi of x equal to 0 is equal to phi I minus V A. This is what the built-in potential with the applied voltage V A. Next, Schottky effect. We know that the barrier formation, till now we discussed about the formation of barrier. Now, how we are going to reduce this barrier? Since if we not going to reduce this barrier, it is difficult for the flow of electrons. So, by applying a proper potential or proper voltage, we can reduce this barrier. This is called as Schottky effect. By applying a proper voltage, reducing the barrier height is called as Schottky effect. In the picture, we can observe the metal and semiconductor and the surface charge due to the contact of semiconductor and metal, and the electrons here. This X indicates the depletion region width, and due to the metal and semiconductor contact, the image charge are formed, the electric field formation in the metal and semiconductor looks like this. And when we are going to apply the potential, when the barrier is reduced and it is depend on the applied voltage, when we are going to apply the sufficient voltage to reduce the barrier potential, the energy band will comes down, it almost reach the interface energy band. So, there is an interface energy also exists between the conduction and valence band due to the contact. So, it is almost reaching the interface energy band due to the application of voltage. So, we are reducing the potential barrier here. This is how when the Schottky effect occurs, the energy band diagram of a MS junction looks. The energy band diagram of silicon Schottky barrier with phi B is equal to 0.8 volt and ND, the donor concentration, is equal to 10 power 19 per cubic centimeter. This is equal to delta phi B is equal to square root of q epsilon of max divided by 4 pi epsilon s, because of the surface area we are calculating. This is the formula for phi B, that is the barrier height. Phi B indicates the barrier height. This is what the formula for a phi B when having a silicon with a Schottky barrier. Next, we move on to another type of diode, that is MIS. MIS means metal insulator semiconductor. Metal insulator semiconductor diode form when insulator is sandwiched in between metal and semiconductor, which forms a MIS diode. The structure of MIS diode looks like this: the metal on top and insulator next to it semiconductor, which may be N or P type. The ohmic contact, there is no potential here. This is called as ohmic contact. The energy band diagram of a MIS diode having a flat band At equilibrium itself it is having a flat band. This is a phi by barrier potential is created. The phi b represents the height of a barrier when metal, insulator and semiconductor are in contact. This phi m represents the metal work function, and chi indicates the electron affinity of a semiconductor. Eg by 2 is the band energy gap, that is divided by 2, and q phi b is this is chi phi b indicates the potential of a semiconductor, and q phi s indicates the potential of a potential when we are going to give for a capacitor. Ideal MIS diode N type, when applied voltage is equal to 0, what is the formula for finding the potential? Finding metal semiconductor potential, that is equal to work function, metal work function minus chi plus Eg divided by 2 q minus psi b, that is equal to 0. This is when we are not going to apply the voltage. When voltage is equal to 0, MIS diode have the metal to semiconductor built in potential. Then for a p type, how the energy band diagram looks like means, here the Fermi level is touching the below the valence band. The conduction band is here, the valence band is here. We can observe the p type semiconductor, the Fermi level band is below the valence band. Same thing, the barrier will be having the phi b of height, and m is a work function, chi is the electron affinity, and this is the formula for a potential of a metal semiconductor of a p type. This phi m minus chi plus Eg divided by 2 q plus psi b, that is equal to 0. Then accumulation, what happens when the applied voltage is below 0 and applied voltage is above 0, what happens for p type and what happens for n type? That is, the applied voltage is not equal to 0, there are accumulation, the charge is going to accumulate. Here in the p type we know the majority carriers are the holes, the majority carriers in the valence band is going to accumulate below the Fermi level when voltage is less than 0 in a p type. When we move to n type, when the applied voltage is greater than 0, the majority carriers electrons will going to accumulate in the conduction band. So, majority carrier in the p type accumulate in the valence band, but in n type it is accumulated in the conduction band. Minority carrier accumulated in the conduction band for p type, and for n type the minority carrier accumulated in the valence band. This is the difference when the voltage is not equal to 0, the accumulation of majority and minority carriers takes place, and due to the accumulation the barrier is going to increase for a current flow. Due to the accumulation of this, we can expect the barrier. Due to this, the current flow is difficult. This looks like this, before it was like this, but after the application of voltage p type less than 0, the barrier will be increased. For n type, for greater than 0, the barrier will be increased like this. For p type, the depletion for V is greater than 0, Fermi level will be next to the interface energy band and below the conduction band. The majority carrier will be moving to the valence band, the minority will be on the conduction band. Same thing for a V less than 0, this is the opposite case what we are discussed in the accumulation. There we discussed the P for a voltage lesser than 0, in the depletion for a V greater than 0. So, for a V greater than 0 means the depletion layer will be increased in a P type. This will makes the current flow difficult. Here when V is less than 0, the Fermi level is reaching the conduction band. So, which will increase the depletion layer. So, it will makes the current flow difficult. So, in inversion is a process where we are going to invert the charges. The majority carrier of P type will be inverted with the minority carriers, and same thing the majority carrier in N type electron will be inverted with the holes. Here the electrons, it has to be holes, as we know P type having a majority carrier holes, but it is inverted with the electrons in the conduction band. As the voltage is increased above the 0, as the voltage is increasing below 0 in N type, the majority carrier in a conduction band electrons will decreased and it will the minority carrier are increased in a valence band. This is the process inverse of a accumulation. Next, p type semiconductor, when applied voltage is not equal to 0, we observe that as a psi positive band bends down, this band will going to bend. This is not a flat band, it is going to bend because of psi. As we increase the psi, the band will going to bend. That is what we observe from p type semiconductor when applied voltage is not equal to 0. These are the some of the formulas that we need to know. The concentration of holes, that is equal to intrinsic concentration into e to the power of minus ei, that is the intrinsic energy, minus Fermi energy divided by k, and T, k is the Boltzmann constant, and that is equal to intrinsic concentration e to the power of minus ie, that is the intrinsic energy, minus q psi minus phi energy, that is divided by kT. This can be simplified and can be written as Np naught, that is into e to the power of beta psi, where beta is equal to q by kT. K is a Boltzmann constant. This is for an ideal MIS p type diode. And as the Cb moves towards EF, when the conduction band moves toward the EF, if psi is greater than 0, that n increases. So, the electron will going to increases as the conduction band moves towards the Fermi energy band when psi is greater than 0. This is the condition for a p type, and this is what the formula, that Pp, that is equal to Pp naught e to the power of q psi divided by kT, that is equal to P naught e to the power of minus beta psi. When Vb moves, the valence band moves away from Fermi energy, if psi is greater than 0, that is P is going to decrease. This is the process of inversion, where from when valence band moves away from the Fermi energy band, when psi is greater than 0, P will going to decreases. Then ideal MIS diode p type will have the sum of this at the surface, the psi will be equal to psi s, the concentration Ns is equal to Np naught e to the power of beta phi s, and Ps is equal to Pp naught e to the power of minus beta psi s. From this, the surface carrier concentration, the surface carriers of holes and as well as electron, the surface carriers of electron, this is the surface concentration of hole. A formula we can find out from the previous slides. So, these are the conditions. When phi is less than 0, accumulation of holes will happen. This is what we can observe from the energy band diagram. Fermi level, it is near to the conduction energy band, and phi s is equal to 0, the flat band we can observe. When phi b is greater than phi s is greater than 0, this is called as depletion of holes. This is how the energy band for it, and phi s is equal to phi b is the intrinsic concentration of holes, electrons and intrinsic region. These are the different concentration, the surface carrier concentration, surface holes concentration, surface electron concentration and intrinsic concentration, intrinsic electron concentration. This is when phi s is greater than phi b, inversion, more electrons than holes, that is what, more minority carriers than majority carrier. This is how the energy band diagram looks for a different phi s. So, the carrier concentration, the surface carrier concentration varying the phi s, we can vary the energy band diagram, and also we can get the accumulation, flat band and depletion or intrinsic concentration or inversion mode. All this can be varied with the help of surface concentration. So, for summary, the metal, we come across the metal semiconductor characteristics and what happens when metal and semiconductor are in contact, how the energy diagram will vary due to the chemical reaction, and the Schottky effects, how we are going to reduce the Schottky barrier with increasing the potential, and metal insulator semiconductor diode, its characteristics with a different applied voltage. Next, some of the questions: how does potential barrier formed in MS junction? What is Schottky effect? How does MIS diode works? For the reference, you can visit the website, and also you can refer the textbook Electronic Devices and Circuits by G.K. Mittal. This ends up the session. Thank you.